Last time we met, we looked at specific heat. We found out water is a good cooling agent because it can hold lots of heat. So any of these three items, joules, grams, temperature change, we might want to be able to solve for if needed. So a sample of aluminum, I had to look at that. Aluminum's like 0.90 joules per gram per degree. C. The sample absorbs 2,500 kilojoules of heat and its temperature increases by 7.5 degrees Celsius. What is the mass of the aluminum sample? So here's our given data, and when I look at that, I always think of units as being conversion factors. So if I start out that way with whatever I'm going to do, I'm going to divide by specific heat, evidently, because that's what the units tell me I'm going to have to do. So now I can just multiply by 2,500 kilojoules. I'm going to have to convert that into joules. 1,000 joules for every 1 kilojoule. Alright, now my joules are doing what they should. One more thing to fix up now. Got to get rid of degrees C, so I am also dividing by temperature. Dividing by temperature, dividing by specific heat. And I didn't have to ask myself those questions at the beginning. You trust your units. So now I can probably go 2,500 times 1,000, divide 7.5, divide 0.9. That's how many grams. That's a big chunk of aluminum. Any questions on this process?
If we were going to do one of those on the quiz or the test, I presume you'll give us the specific heat, or do we need to memorize?
You don't need to memorize something like that. Doing up problems, you should have waters memorized. 4.184 joules per gram per degree C. So Friday, you had your crash course on Hess's law with that one example problem. So here's this idea of a series of steps again. If a reaction is carried out in a series of steps, change in enthalpy for the reaction is the sum of the change in enthalpy for each one of the steps. And so here we're looking at the combustion of methane. That's one of my favorite. I like heating my house with natural gas. And you can see here it is, negative 890 kilojoules. When it comes down to these products here. Now what's this? This is when we form carbon monoxide. So we can think of the combustion reaction maybe occurring in two steps. The first one, half oxygen and 2 waters here, and then we add another oxygen molecule to the carbon monoxide and get to CO2. And this occurs, and sometimes this last step maybe doesn't occur so well. That's why you want your hot water heater and your furnace to be nicely vented so you don't breathe any CO2. But the main point of this is the enthalpy change here and the enthalpy change here sum up to this one over here, negative 600 summed with a negative 280 sum up to 890. Enthalpies of formation. They're tabulated in the back of your book. They're very useful. What are they? An enthalpy of formation is defined as the enthalpy change for the reaction in which the compound is made from its constituent elements in their elemental form. So basically, it's heat given off when we can form a compound from the elements. And here's just a small table of what you have in back. You can look up this compound, and here's its heat of formation. And you see a bunch of different ones here, and they're all tabulated away. So first, let's look at this idea that any reaction, you can break it apart into a series of steps. Here we have the combustion of propane. So here's our propane, and we can imagine propane being broken down into carbon and hydrogen. Here's CO2, and we can imagine CO2 being formed from graphite and oxygen. And here's water, and we can imagine water being formed from hydrogen and oxygen combining to form H2O. So notice I have elements in their elemental form, elements in their elemental form. And if I sum these two equations, let me just do something for fun. I can probably come over here and say the graphite would cancel out, 4 hydrogens would out, oxygen doesn't. I have 3 and 2, and sum up for 5. There's my, so those are the species that cancel out, and here's my overall reaction. So let's just go back. An enthalpy of formation is defined as an enthalpy change for the reaction in which a compound is made from its the elements that are found in it. And we said at one point in time that enthalpy was a state function. And so chemists have defined an element in its elemental form to have an enthalpy of formation of 0. And one of the definitions of an element is when you break down a compound and you can't break it down any further once you break it down into its elements. So chemists said, well, let's just imagine elements always existing, or you can't break them down any farther. Let's give them an enthalpy value of 0, standard enthalpy of formation of 0, and then we can combine them, like burn hydrogen and oxygen, form water, measure the heat, and then in a table here, right here, we can tabulate this. There's the enthalpy of formation of water when it's formed from its elements. And I don't know why I put this graphic in here, other than it kind of shows that stair step, only it doesn't look like much of a stair step. But here's our propane and oxygen, and we can imagine getting them back into their elemental forms and forming some CO2, and then finally bringing these two elements together and forming some water. So all these steps here are going to sum up to this step here. Or perhaps we can measure this step, and this step, and we want to deduce the heat of reaction. So I said Hess's law is amazing because we can calculate the heat of the reaction, and we don't have to go into the lab and actually perform the experiment to figure it out, because people before us have done all these experiments and tabulated the heats of formation. And I sometimes tell students that a law always gives you the same results, and it's typically like a number, like the law of conservation of matter. The products always weigh the same as the reactants. The law of gravity, falling bodies always fall with the same acceleration due to the gravitational constant. Everybody would measure the same acceleration or the same constant. So Hess's law is a law in that these heats of formation are tabulated. You can come up with a reaction, calculate the heat of formation, then you can go in the lab and measure it, and it comes up the same number, or at least within any experimental error. So the take-home message of all that is we can take and calculate a heat of reaction if we sum up the heats of formation of all the products and minus summing up all the heats of formation of the reactants. And so these numbers here are the stoichiometric coefficients in the balanced chemical equation. So this looks a little messy. I just realized I got way too much information on this slide. But we'll look at an example here in a second. So this 3 says I'm going to go 3 times the heat of formation of carbon dioxide, which is roughly negative 392.5. Sum that with 4 times the heat of formation of water, which is negative 206 roughly. And then I'm going to minus the heat of formation of propane, negative 103.85 kilojoules, and 5 times the heat of formation of oxygen. And why does oxygen have a heat of formation of 0?
Because it's an element.
Right, because earlier when I was talking about state functions, chemists have stated, let's call the heat of formation of an element in its normal elemental state 0. We can't break anything down further than an element. So here's a good example problem. Here's a reaction, and we look in the back of the book, and we look up the standard heats of formation. So what was that equation? I saw everybody trying to write down real fast. Big summation sign, and I don't know if it started with M or N. How about N? Most important part is its products minus summing up. There's a horrible summation sign. React. That's the most important part. Alright, so we're going to start right here. I'm going to look up here and I see a 2. So I need to go 2 times the negative 200. And that summation sign says we sum these up. The M was the 2 there. And I see a 1. I normally don't bother with that, but I want everybody to see that. So the coefficients times the heat of formation all sum together. And we've done that for the reactants.
So,
the products. And now we need to minus the reactants. So I see a 3 there. I'm going to go 3 times 34, summed with 1 water, negative 286. So products first, minus the reactants. And you can see with maybe the negative and the negatives, really easy to make a sign error. That's why I kind of like to write those above the species and then go through and do products, sum them all up, minus the reactants, sum them all up. So I just might go 2 times a negative 207 plus a positive 90. There, I've summed up the heat formation of all my reactants. Now let me do my products over here. I'm going to go 3 times 34 plus a negative 286. So now I go a negative 324 minus a negative 180. And I did it all perfectly on my calculator with the signs in there. So it shouldn't give me any headache. Looks like it is. No, it's not.
no.
Have faith in yourself, Eric. And sometimes when I'm in a hurry and I get ahead, I look at this and say, oh, this is going to be positive value, and it's going to lower this by that amount. You want to make sure that makes sense. And this is the kilojoules per mole. And we'll assume everything went correctly because our answer was one of the answers listed. However, a lot of times one thinks of every way you can do it wrong and does it wrong and gives you those for alternate answers than the correct one. All right, any questions on using heats of formation to calculate a heat of reaction? So now you've had the heart of Hess's law and what good it's used for. So this might be kind of a review a little bit and some more things tied in, let you see it a little different way. Hess's law states that the change in enthalpy for a stepwise process is the sum of the enthalpy changes for each of the steps. And here we're just seeing basically a phase change where this reaction has water in the liquid form. We want it in the gaseous form. Here's another step to do that. The associated enthalpy gets us there. And here's this stepwise thing. This distance is the sum of these two distances. Here's where we just have the water and the gas, but we go this little extra step to get down here. And now these two steps sum up to that step there. There's probably a couple things we haven't seen. Manipulating thermochemical equations in a manner that gives the overall desired equation. Remember the rules for manipulating thermochemical equations. Always specify the physical states of the reactants and products because they help determine the actual enthalpy change. When multiplying an equation by a factor n, multiply the change in enthalpy by that same factor. Reversing the equation changes the sign but not the magnitude. Add the change in enthalpy for each step after proper manipulation. And we can use this to find enthalpies that cannot be found directly, maybe experimentally. It's kind of hard to do. Alright, so let's see here. NO plus ozone going to NO2 plus O2. Let's change in enthalpy. Like this. A weird fraction. I knew we needed more practice with fractions in the change in enthalpy. Here's O2 going to oxygens by themselves. How interesting. Alright, can we go from NO plus O gas to NO2? So this idea of something we can't do directly. Maybe we always see oxygen being diatomic, and the only time it's not is in some weird reaction where we can't really isolate it or use it as a reactant. So this might be a chemical reaction that's hard to pull off. But it might happen, like up in the upper atmosphere, and we want to know what the enthalpy change is. So we have NO as a reactant with the correct coefficients. So we write this equation just as is. The second equation must be reversed so that the ozone, O3, introduced by the first equation will cancel. O3 is not part of the overall chemical equation. So we change the sign of this, and now these two steps sum up. And here's an interesting thing here. We can put a coefficient of 1 in front of here and call it 2 halves. And then we can go 1 half minus 3 halves to get to our 1 half there. That's how that ended up. And now we have this overall equation. So then we need to deal with that. We take that last equation. So we divide the third equation by 2 and reverse its direction. As a result, we must divide the change in enthalpy by 2. And finally, we get the sum of all the steps, and we're able to add them together, and this is what we finally end up with. Think about it. Double check it. Any questions?